Hello everyone. So, we're going to take what we learned last time about momentum and now we're going to apply it to angular momentum, to rotational motion. Okay? Honestly, it's so interesting. We've experienced this before when we made a transition from linear motion to rotational motion. There are so many similarities, we just kind of redefine things. Okay? So the first important thing to remember is that torque is kind of our equivalent to force as far as rotational motion goes. And we have inertia, which is going to be comparable to mass in this idea that we're working with today. Okay, inertia is a property of matter, right? And so more mass, more inertia. And we're going to work through this process and see a similar connection between force, remember when we did the linear component, between force and momentum, and then torque and angular momentum. Okay, so let's start with our angular acceleration, which is this alpha, and that is a change in omega, which is our angular velocity over time. So just like with linear acceleration, which was a change in velocity over time, our angular acceleration is a change in angular velocity over time. Okay? And then if we substitute torque for force in Newton's second law and do a little rearranging, we have that angular acceleration is equal to net torque, or sum of the torques, over mass, which we're substituting inertia. Okay? So let's make this substitution. As in, if these are both equal to acceleration, then we can set them equal to each other, right? And if we have two fractions that are set equal to each other, we can cross multiply. And so this angular velocity multiplied by the inertia is going to equal the time component multiplied by the net torque. So we get this net torque multiplied by the time component, and that's going to equal the inertia multiplied by that angular velocity. I want to draw below this the linear equivalent to this, which is force multiplied by the time component, and mass multiplied by velocity. Okay, so see how we have our impulse and we have our torque equivalent to force. So this is angular impulse, and then on this side we have mass or inertia and multiplied by velocity or angular velocity. So that's our momentum, and it's an angular momentum, which we represent with the letter L. Okay. So inertia multiplied by the moment of inertia multiplied by the angular velocity. Okay. So angular impulse, this is that delta. We worked through this very similar where we distributed the delta, and so what we ended with was torque delta T is equal to IW final minus IW initial, which is just angular momentum final minus initial, L final minus L initial, which is just delta L. The angular impulse is equal to the change in angular momentum. Okay. One important difference here is when we are calculating this angular momentum, we do have it as a vector component, and when we multiply our two values, our moment of inertia and our angular velocity, we have to use the right hand rule. And so what this looks like here is saying if we have our angular velocity and we're to take our right hand and it's like if this is rotating this way, and so we're wrapping that around, then the momentum is actually pulling it that way. And then if it was rotating the other way, according to the right hand rule, then our momentum would be going the opposite. Okay. We also talked about moment of inertia as far as the figure skater goes. And we talked about how if we bring mass closer to that axis of rotation, that we have a change in that moment of inertia. And so it causes them to spin faster. It's easier to spin. And so we have that similar concept here with this rotational component of momentum. Okay? All right. So that's our small little bit about the rotational component. Now, is the momentum of a car traveling to the south different from that of the same car traveling north at the same speed? Let's think through this. It's asking for momentum. Momentum is mass times by velocity, and we're talking about velocity as a vector, so that means that momentum is a vector as well. So the mass is the same, the velocity is the same magnitude, opposite direction, and so that would be the same for our moment of inertia. It'd be the same magnitude, but opposite direction. So that would change our sign from like positive to negative, or it's a direction component altogether if we represented this vector with an arrow. So we have momentum of a car traveling to the south. Okay. So that would be our momentum vector, which is the same direction as our velocity vector. Is that different from a car traveling to the north? Same magnitude, but opposite direction. Same with our velocity. And so is it the same? Magnitude is the same. The direction is different, so the vectors themselves are different. Example number 3. You're playing an exciting game of egg toss at your family reunion. Explain why the best strategy is to catch the egg without breaking it. Involves moving your hands inward to catch. Okay, for this one, focus on impulse, and I want you to hit pause, write down some thoughts, and then come back to it, and let's see if we have the same answer. Okay, so we know that impulse is a change in momentum, that force times by the time that it's applied is equal to a change in momentum. And that change in momentum is going to relatively be the same, right? Because it's going from some initial velocity to 0 velocity. So we have this change in momentum. It has to come to 0. And so this whole component's not going to change, but we can adjust what portion is force and what portion is time. So we could have the same change in velocity or momentum if we have a large force over a short amount of time, or a small force over a longer period, bigger period of time. And so that's the advantage of when you're catching it, pulling your hands back, because you're extending the amount of time, which means you're reducing the force that's on the egg, and so it's less likely to break. Okay, and now we have example number 5. I'm going to split this up into 2 videos. So we will do example number 5 as a video itself, and so then there'll only be 2 videos for today. Okay? So that's a plan. Give number 5 a go, and then come check the second video to see if you're getting the same answers.